Welcome to today's Explainer. When we hear the words acid and base, we rarely grasp the true scale of what's actually happening. But today, we're going to explore how acid-base chemistry is literally the hidden operating system of our entire world. It's running in the background of almost everything around us, scaling all the way from invisible quantum mechanics up to global environmental engineering.
So think about this for a second. What actually connects a drop of sour rain falling from the sky, the tightly coiled DNA inside your living cells, and a billion-dollar industrial wastewater plant? I know, it sounds like the setup to a really strange riddle, right? Well, the answer is incredibly elegant. It all comes down to the simple transaction of subatomic particles. Today, we're going to decode exactly how these fundamental atomic rules end up dictating biology, economics, and ultimately our planet's survival.
Okay, here's our roadmap for the journey. We'll start with the evolution of acids and bases, look at acid-base equilibrium and titration, dive into life-saving buffer systems, and uncover the secrets of biopolymers. Then, we'll scale way up to the magic of organic synthesis, and finally, sustainable green chemistry. Let's get into it.
Section 1. The evolution of acids and bases. The microscopic rules of the game.
Now, our understanding of these microscopic rules definitely didn't happen overnight. Back in the 19th century, Arrhenius gave us our very first rulebook. Basically, acids release hydrogen ions in water and bases release hydroxide. It's simple, sure, but it really only worked for water-based liquids. Then, jumping to 1923, Bronsted and Lowry totally changed the paradigm. They realized it's actually a dynamic game of catch. Acids throw a proton, bases catch it. And this was a huge deal because it meant even gases and non-water liquids could play along. Finally, Gilbert Lewis zoomed past the proton entirely. He focused on the true currency of chemistry, the electrons.
And what makes the Lewis theory so brilliant is that it acts exactly like a microscopic economy. If you think of electrons as chemical currency, a Lewis base is kind of like a wealthy investor. They're super eager to donate a pair of electrons. A Lewis acid, on the other hand, is the hungry startup. It's starved for electrons and eager to accept them just to build a stable bond. So there are absolutely no protons physically moving around here. It is a pure financial transaction of quantum orbitals.
Section 2. Acid-base equilibrium and titration. The mathematics of equilibrium.
So how exactly do you track these invisible electron transfers? Well, you use equilibrium and titration. Now, normally, chemists just use color-changing indicators to find the exact neutralization point. But what if your solution is totally cloudy or murky? You can't see the color change. So you use electricity. In conductometric titration, we measure the solution's ability to conduct a charge as we slowly add our neutralizer. But here's the catch. As you add liquid, you're obviously diluting the whole mixture, right? And that artificially lowers the conductivity. So step 2 is absolutely crucial. Scientists have to apply a clever mathematical correction coefficient, which is the original volume plus the added volume divided by the original volume, just to erase that physical dilution effect. And only then does the true equivalence point actually reveal itself in the data.
Section 3. Life-saving buffer systems, the biological thermostats.
Okay, let's move out of the laboratory beakers and straight into your circulatory system. Your blood actually operates this incredibly elegant biological thermostat called the bicarbonate buffer system. Human blood absolutely must stay near a pH of 7.4. If acidic metabolic waste suddenly dumps into your bloodstream, this system stubbornly absorbs it. And the secret here lies in a dynamic dance between carbonic acid and bicarbonate. Together, they act like a massive chemical shock absorber to protect us against fatal physiological crashes.
To put that into perspective, according to the Henderson-Hasselbalch equation, for human blood to maintain that perfect 7.4 pH at normal body temperature, the ratio of bicarbonate to dissolved carbon dioxide must be exactly 20:1. Seriously, 20:1! It is an incredibly fragile, mathematically rigorous tightrope walk, and it's required every single second just to maintain human life.
So why does this work so flawlessly? Well, it's because unlike a glass test tube, the human body is an open system. In a closed lab beaker, chemical byproducts just build up until the reaction literally chokes itself out. But your body breathes. When acid spikes, your bicarbonate converts it to CO2, and your lungs simply exhale it. At the same time, your kidneys are continuously pumping out excess hydrogen. When this brilliant system fails, say because of hyperventilation or kidney disease, we see the severe physiological consequences of acidosis or alkalosis. It is literally chemistry directly dictating biology.
Section 4. Secrets of biopolymers, the electrostatics of life.
Let's zoom in even further, right past the blood and straight into the nucleus of your cells. This number, 4.0 to 4.5, represents the isoelectric point, or pi of DNA, and that is incredibly acidic. What that means is, at our body's normal, neutral pH of 7.4, DNA carries a massive negative electrical charge, and that is actually by spectacular design. Because DNA is so negatively charged, it acts like a powerful magnet, wrapping itself incredibly tightly around positively charged histone proteins. This electrostatic attraction is literally the only way you can compress 2 whole meters of DNA into a single microscopic cell nucleus.
Now what happens if just one tiny electric charge goes missing? We'll take a look at sickle cell anemia. In a normal, healthy hemoglobin protein, the 6th position is an acidic, negatively charged molecule. But a genetic mutation swaps it out for valine, which is totally neutral. Losing that single microscopic electrical charge sets off a devastating butterfly effect. Without the proper electrostatic repulsion, the proteins just stick together. They violently warp the entire red blood cell into a sickle shape. Just one lost charge completely changes a life.
Section 5. The magic of organic synthesis. Engineering molecular architecture.
All right, from the delicate fragility of single amino acids, we're going to jump in scale to the brutal forces of industrial synthesis. To build complex things like pharmaceuticals and plastics, chemists use what's called the Friedel-Crafts reaction. Now, a benzene ring is incredibly stable. It really doesn't want to react with anything. So to force it open, we have to use aggressive quantum chemistry. We introduce a ravenous Lewis acid catalyst, like aluminum chloride. This stuff is so starved for electrons that it violently rips an atom apart just to create a highly reactive carbon molecule. That molecule then forcefully crashes right into the benzene ring to create a brand new carbon bond.
But engineers face a massive choice in how they actually use this reaction. Alkylation is, well, it's chaotic. The molecules are constantly rearranging themselves, and once the reaction starts, it often overreacts, attaching way too many molecules to the ring. It is really difficult to control. Acylation, on the other hand, is elegant. It uses a chemical structure that stabilizes the intermediate state, and then it actually deactivates the ring after just a single molecule attaches. This is a huge deal because it gives pharmaceutical manufacturers exact, precise control over their molecular architecture.
Section 6. Sustainable green chemistry. Planetary scale engineering.
Now, let's zoom all the way out to planetary scale engineering. Imagine you're running a gigantic industrial wastewater plant. Millions of gallons of toxic, acidic water are pouring in every single day. You absolutely have to neutralize it before releasing it back into the environment. So what do? Do you use sodium hydroxide, which is a highly soluble liquid, or do you go with calcium hydroxide, an insoluble powder we commonly call lime?
This is an incredibly intense economic and engineering dilemma. Sodium hydroxide is super expensive, and you actually need 42% more of it to get the job done. But it leaves absolutely no sludge behind. Lime, on the other hand, is cheap and highly efficient, but it leaves behind mountains of physical sludge that you then have to pay to dispose of. However, consider the impact on bacterial biofloc. The calcium in lime actually helps beneficial bacteria clump together to clean the water naturally, while sodium hydroxide just disrupts them through electrostatic repulsion. So a simple chemical choice literally dictates your entire budget, your waste management strategy, and the health of your biological organisms.
So what actually happens when a massive plant runs the numbers on this? Well, one facility actually switched from liquid sodium hydroxide to solid lime. And even when they factored in the cost of buying new heavy machinery and paying for extra labor just to handle all that physical sludge, they saved so much money on the raw chemical costs that their return on investment was a jaw-dropping 2,410%. They recovered all of their massive capital equipment costs in just 4 months. I mean, that is the pure power of chemical economics at scale. But looking forward, our future really relies on eliminating toxic waste entirely. And that brings us to the absolute magic of green chemistry: zeolites. Zeolites are solid acid catalysts that basically look like porous sponges at the microscopic level. And they are incredible. They have these nanoscopic channels that only let perfectly shaped molecules escape. By swapping out individual atoms with metals like titanium or zirconium, scientists can create highly customized Lewis acid sites. And because they're solid, they don't produce any toxic sludge. You just filter them out and bake them at a high heat to revive them. But here is the most exciting part. We are now using these custom solid acids to capture raw CO2 greenhouse gases and turn them directly into pure ethanol fuel. It's practically a climate miracle.
So, as we've seen, the concepts we've explored today connect literally everything, From quantum electron orbitals trading invisible chemical currency, to the delicate 20-to-1 ratio keeping your blood pumping, all the way to the massive climate-saving bio-oil refineries of tomorrow, it is all a single continuous thread of scientific discovery. Acid-base chemistry is definitely no longer just isolated to a beaker. It's the fundamental tool for decoding life itself and engineering the survival of our planet.
So I'll leave you with this final thought. If we are already manipulating these foundational atomic rules to literally turn the greenhouse gases heating up our planet into the very fuel that could power our future, what other boundaries are waiting to be broken? What other planetary limits could we rewrite using nothing more than this simple, beautiful transaction of an electron or a proton? Thanks so much for joining me on this explainer, and keep questioning the chemistry of the world around you.